about his relativist phase. So that's not philosophical relativism, but relativist as in the community of people who study general relativity. And that's a term they use themselves. Wheeler was the chief architect of what had been called the Renaissance of general relativity. From its development by Einstein and others in the 19-teens and 20s until the 1950s, relativity hit what was called a low water mark by Gion. It was seen as abstract, perhaps better suited to mathematicians than physicists, and detached from the rest of physics. Wheeler injected a new energy into the field. Terry Christensen, in his dissertation, has detailed the central role Wheeler played as a pedagogue in this renewal, and studied his generations of graduate students and the work that they would go on to do. Wheeler organized conferences, supervised dissertations, and published prolifically on issues of relativity. His program was known as geometrodynamics, in analogy to electrodynamics. Wheeler saw the study of gravity as the study of the dynamics of geometry. This work is in stark contrast to, for example, Stephen Weinberg's field theoretical approach to general relativity. Wheeler also coined the terms black hole and wormhole to describe exotic gravitational phenomena, some of which I'll mention later on. Wheeler saw gravity as at the heart of physics, and he saw the vacuum in various guises as at the heart of gravitation. So, this is a sketch of Wheeler's ontological progression, and it's also the outline for my talk. We're going to start by talking about his thesis that everything the world is made of only fields of zero rest mass. We're then going to talk about his view of the seat of reality being sort of quantum foam. And then I'm going to skip most of the intervening years between 1962 and 1971, where he was concerned with something called superspace, and talk about pre-geometry. The epistemological principles that Wheeler used in his work, and by this I mean sort of his rules for deciding what course to take in figuring out about the world, right, can be sort of characterized as a radical conservatism and a search for simplicity. So rather than unity as a heuristic, as we heard in the last presentation, simplicity here was a motivating concern for Wheeler. Writing from Los Alamos on 18th July 1953, Wheeler jotted notes on the philosophy of approach to elementary particle problem, and he exhibited his radical conservatism, a willingness to take existing concepts as far as possible before introducing new ideas. He began by noting that humor equals humbleness and willingness to find self-wrong to learn. And this really emphasizes the sort of non-dogmatic approach. Wheeler saw himself as asking questions, and he literally formed his proposals in terms of questions, rather than setting out dogmatic proposals saying this must be the way it is. He would tend to pose questions that he thought would be revealing, and clearly thought would force physicists to come around to his side of thinking. It also demonstrates that Wheeler really found joy in his work. At this time, Wheeler was preparing to give a series of talks in Tokyo, and was thinking about the path he would take for his presentation there. So he wrote in his proposed Tokyo program, be as conservative as possible about introducing new elements into description. Make basics as clean and simple as possible. It is only the consequences that are complicated. Ice, elementary particles, meteorology, geology. So here he's referring to, for example, the fact that simple seeming equations of fluid dynamics in a way govern the entire climate, right? That the laws can be simple, but the consequences can be complicated. So I'm going to start by talking about zero rest mass fields. In particle physics, each field considered on its own is considered by two terms in an equation called a Lagrangian. We heard a little bit about in Tillman's presentation. One term is called the kinetic term and roughly describes the motion of the particle through space. The other term is called the mass term and describes the behavior of the particle at rest, roughly. In the case of some particles, however, there may be no mass term. The field may be massless, or be a zero rest mass field. The paradigmatic example is the photon, the particle associated with the electromagnetic field. Photons have zero rest mass. In a sense, all of their energy is always in motion. A counterexample is the electron and its associated electron field. Electrons can be stopped in place, at rest. There is a sense in which a space that is filled only with zero rest mass fields is still a vacuum. For example, spaces filled with zero rest mass fields were referred to by Wheeler as empty. So for Wheeler himself, a space that is full of stuff is still a vacuum. And in fact, if we think of a picture of, say, interstellar space, there's light moving through it, it's a zero rest mass field, but we still consider that a vacuum. As Tillman mentioned, there are vacuum solutions to the field equations of general relativity. So this is, I would argue, a picture of the vacuum. So Wheeler considered the fundamental problem of elementary particle physics to be where do particles come from and what governs their relations, or the coupling constants that describe their mutual interactions. Wheeler started his reflections on how geometry might solve the problem of explaining the existence of elementary particles in a notebook at the American Philosophical Society archive, devoted to quantum electrodynamics on 11th October 1953, writing from Princeton. Under the heading, Attempts at a Unified Theory, he wrote that his Japanese visit emphasized difficulties of the view that each particle has a field associated with it, and suggested the alternative view that only the field of zero rest mass should be regarded as fundamental. As an example, he proffered the electron, which was to be regarded as, quote, no more fundamental than any other particle, given the picture of the electron as a zero rest mass neutrino with a charge loaded on its back. As he had months earlier, Wheeler insisted that he, quote, be conservative. And here, that meant, quote, taking electromagnetism and gravitation seriously down to the very smallest distances. Here, Wheeler thought that he had to take physics seriously to the smallest distances because of the integrals involved in calculating the quantities in physics. Later, he would use the development of black holes as a more physical motivation for this sort of thinking. At the turn of the new year, on January 19th, 1954, Wheeler made 10 copies of a working paper at Los Alamos to circulate among close colleagues. This preprint encapsulates many of the ideas detailed above, including the belief in the fundamentality of zero rest mass fields and Wheeler's radical conservatism. It was entitled The Zero Rest Mass Field Fundamental Field, the Zero Rest Mass Fundamental Field Hypothesis. And according to the chronology I've established, this is the last example of Wheeler's initial ontological view of the vacuum. He began, an attempt is made to assess the hypothesis that each elementary particle is a disturbance in a common fundamental field or system of fields of zero rest mass, the electromagnetic field, the gravitational field, and the neutrino field. It should be noted that until the mid-90s, physicists believed neutrinos to be massless. There's since been evidence that they have a very small mass, but for Wheeler at this time, the neutrino was massless. Wheeler here was swimming against the grain. Quote, this picture is the direct opposite of the view that a new characteristic field of finite rest mass is associated with each elementary particle, and that with n particles are associated n times n minus 1 over 2 primordial coupling constants. The first paragraph of this preprint ends with a striking expression of what I have called his radical conservatism. To renounce free experimentation of ideas is the ideal in mind. Instead, the goal is to extend the domain of application of the already existing and solidly grounded theories of electromagnetism, of gravitation, and of quantization. It appears reasonable to believe that from these ideas there follows a network of consequences far richer than past limited investigations have so far sought out. Until these consequences have been explored, it seems premature to invent new ideas to deal with the elementary particle problem, or even to assume that invention is going to be needed. So here Wheeler sort of clothed a pretty radical hypothesis, an ontological picture where only zero rest mass fields could produce all of reality, but he clothed it in a conservative argument, saying, well, you think you need to invent a new primitive ontological object for every particle you find in a new accelerator, and I'm telling you we don't. Or I'm thinking along those lines. Wheeler would eventually ask whether a unified theory of gravitation and quantum mechanics that explains the existence of particles could come out of a basic quantum foam at the seat of reality. And as I said before, I say he would ask this because Wheeler would literally formulate his proposals as questions. Befitting his radical conservatism, he did not see himself as pushing bold proposals onto his fellow physicists, but rather as asking questions that revealed the presuppositions already extant in their experimentally verified theories. So we have an experimentally verified theory of gravity, we have an experimentally verified theory of electromagnetism. I want to skip a little bit and just tell you sort of what Wheeler meant by quantum foam. He developed a few metaphors for this, the most powerful of which may be the image of an aviator flying above an ocean. From high above, looking at large length scales, the aviator sees a smooth surface, analogous to the smooth manifold of space-time observed when studying macroscopic distances. If the aviator swoops down closer to the surface, she will observe waves propagating and interfering with one another. These waves represent gravitational waves, and also the ripples in space-time caused by the existence of distributions of matter and energy. Closer still, an aviator equipped with a telescope may zoom down to the millimeter scale and observe foam at the tip of breaking waves. At these shortest distance scales, the regular surface of the ocean is disrupted. If the ocean can be thought of as a flat, two-dimensional sheet, the foam contains structures of other dimensionalities, three-dimensional structures of bubbles. Still at the microscale, bubbles in the foam are constantly being created and destroyed, and connections between neighboring parts of the water are being opened and closed. This smallest scale represents Wheeler's picture of the quantum nature of space and time, frothing with quantum fluctuations like the vacuum of traditional quantum theory. Wheeler was drawn to this picture by two developments. His investigation of what he called Gions in general relativity, and a result found by his graduate student Charles Misner. Misner's result was the rediscovery that because distributions of mass energy create ripples in space-time, one can read off distributions of mass energy from studying the gravitational field alone. So this, Hugh Everett christened this already unified field theory, where you can take electric field lines in space, you can correlate those to the field tensor, the energy momentum field tensor in general relativity, and you can take that to the geometry of space-time. And so it says at the bottom, you might not be able to read it, but starting here, in brief, the electromagnetic field leaves its footprints on space. Moreover, these footprints on the metric are so specific and characteristic that from them one can work back and find out all that needs to be known about the electromagnetic field. One has a purely geometrical description of electromagnetism. In their joint paper, Misner and Wheeler explored a radical new ontological picture. The two views of the nature of physics stand in sharp contrast. The space-time continuum serves only as an arena for the struggles of fields and particles. These entities are foreign to geometry. They must be added to geometry to permit any physics. And then two, there is nothing in the world except empty curved space. Matter, charge, electromagnetism, and other fields are only manifestations of the bending of space. Physics is geometry. And their long paper would go on to explore as fully as possible this second option. The other origin of Wheeler's quantum foam picture was his Gion work, as I said. The Gion idea was to investigate concentrations of electromagnetic radiation, light, a zero rest mass field, that were so dense they would hold together under their own gravity. He would come to call this mass without mass. Because from far away, a Gion looks like any other massive object, but it consists only of fields of zero rest mass. So it's massive, it behaves like a massive object, but it's made of something with zero rest mass. This is mass without mass. This actually satisfies some of the conditions that Einstein was looking for. Wheeler was explicitly philosophical in his introduction to the Gion paper, saying that this was finally the sort of realization of the Newtonian concept of body that didn't involve singularities. So it didn't need singular points, right, to discuss mass. Wheeler maintained his philosophy of radical conservatism during this period, and Gion's were consistent with it. In a letter to John von Neumann sent 12 October 1954, Wheeler wrote, "Dear Johnny, I am still trying to understand elementary particles in terms of existing concepts. The general philosophy is this: how does one know what to invent, or even that invention is necessary, until one has explored further the rich consequences of what one already has? For example, you will see from a quick glance at the enclosed manuscript, which didn't survive, but was probably the manuscript of his Gion paper that was published, that out of gravitation and electromagnetism, or neutrinos, or both, one can construct very interesting models for elementary particles, Gions." Wheeler noted that he and most physicists had tacitly assumed that the space-time manifold of relativity was simply connected. Simply connected manifolds are those without holes or loops. The surface of a sphere is a simply connected manifold. A punctured sphere is not. It was this concept of the possibility of non-simply connected spacetime that was one of the foundations of Wheeler's views on the vacuum as a quantum foam. Wheeler's letter to von Neumann continues. There we go. If this line of reasoning has any value, it suggests that one might understand the existence of electric charge not through the presence of real carriers, but through the existence of multiple connected topologies in the space-time continuum that permit the electric lines of force to continue without end. So here's a diagram that Wheeler drew to indicate what he meant. So here we have the flat sort of manifold of space and time extending out here, but instead of being a perfectly flat sheet, it's not. It's multiply connected. There's a tube here, right, that's running and connecting. And Wheeler realized that through those tubes could run electric lines of force. So that, again, instead of needing a singularity to speak about a charged point, Wheeler was describing just curved empty space, vacuum solutions of the Maxwell equations, vacuum solutions of Einstein's equations of general relativity, but in a non-simply connected manifold, and producing charge. So this, from far away, would look like a point charge, but from very close up, it would appear as part of this multiply connected space. However, this picture is not quite yet a foaming sea. This is just a stable set that is described classically. But once one has crossed into the quantum world, quote, one is forced to recognize the existence of fluctuations in all fields. While at large distances, fluctuations of the metric were considered irrelevant, the mathematics of point charges required integrating over regions, quote, including regions of the very smallest spatial extension. Wheeler at this point was appealing to a formal requirement about integration to motivate following physics down to the smallest scales, and as I said earlier, later he would use gravitational collapse of black holes as a physical motivation for that. Here, the inevitable fluctuations force on space-time. A most complicated structure. Because it is the essence of quantum mechanics that all field histories contribute to the probability amplitude, the sum, and here we have a sum in Feynman's mode of quantizing, where you take a sum over all conceivable relevant field histories and then have an exponential with the classical action for each field history. So because it is the essence of quantum mechanics that all field histories contribute to the probability amplitude, the sum not only may contain doubly and multiple connected metrics, it must do so. In general relativity quantized leaves no escape from topological complexities, of which the figure on the previous slide is only an oversimplified symbol. So there's that again. In 1956, Wheeler took up a position as a visiting scholar at the Institute Lawrence in Leiden, Netherlands, for several months. He brought 3 others with him, Charles Misner, Peter Putnam, and Joe Weber. Wheeler, in conversation with his students, continued to search for a quantum theory of gravity along the lines of his Gion paper. In his notebook, he reported that he, quote, have to sum over all contortions of gravitational field and electromagnetic field, but take only the zero energy part. Here, vacuum fluctuations were seen as more basic than the electromagnetic field itself. Quote, vacuum polarization, a fundamental property of vacuum, not merely an electron field. 3 days later at the Institute Lawrence, while attempting to write up his ideas for a conference in Rochester, Wheeler asked, how come mass of vacuum vanishes so exactly? It seems fantastic this should come out. Is it defined as the answer or calculable? Would be an enormous triumph to get a simple proof. And then, the vacuum has no mass. However, Wheeler had a growing dissatisfaction with his picture because of the lack of calculations and results to come out of it over the number of years. I'm skipping over the development of the theory of superspace, which is the concept of the space of all possible space-times. So you would have a point in superspace could represent a sphere, a neighboring point could represent a torus, a neighboring point to that could represent a 2 torus, and etc. up to more complicated topologies. And there's some fascinating material in his notebooks on superspace that led him through considering the early modern philosophy of Leibniz and monads, but I won't have time to get into that here. So I'm going to skip to the early morning of April 1971, where Wheeler, in bed, was visiting the Battelle Center in Seattle. Wheeler sought to, quote, capture the heart of the puzzle and lay it out in a few perfect words. Sorry, there's a lot of text here, but he reflected that his late friend Leonard Schiff had once called him, quote, the poet of physics. He said in his notebook, in this spirit one searches. It is difficult for me to believe that geometry, quote, simple three-dimensional geometry, is the foundation of it all. Rather, it is only a way towards the goal. Geometry, electricity, and magnetism, and all the persistent, uniform, submerged structure, so structure and matter, must be built out of something far simpler. Here, geometry itself had moved definitely off center stage of the ontological picture. Wheeler came briefly upon the idea of basing his pre-geometry on binary elements. He was strictly guided by his epistemological principle of simplicity. Quote, if going for simplicity, go the whole way. Build out of simplest of all, the yes-no element. Rich Werner proposed this to me at Cincinnati conference 2 years ago when I put the issue to him, as I do to so many. However, it may be, sorry, I ended that quote. However, it may be that this was too simple. A binary calculus is a very restricted language with a limited possibility of expression. Wheeler was led back to philosophy, but rather than turning to early modern metaphysics, as he had while considering superspace, he turned to modern formal logic. At 8 a.m. Eastern Standard Time, Saturday, 10th April 1971, I love Wheeler's notebooks. He dates and times them, it's amazing. He has great handwriting, it's just a pleasure. He recorded when he was in flight from Chicago to New Jersey, which is why the time zone is there. He recorded the first mention of the proposal for pre-geometry he would pursue for the next stage of his career. Pre-geometry would be the calculus of propositions. He began, quote, the simplicity and beauty of the universe are surely dazzling. How get at this dazzling central machinery? More than anything, the right philosophical principle should be the guide today, as equivalence principle was earlier. Collapse, i.e. the formation of black holes, tells one it can be believed that 1, space can come down to Planck size. There is no such thing as space-time or time. Then he skips to 3. Even space geometry itself cannot be more than an approximate idea. 4, coming out of gravitation and electricity and magnetism and spin 1/2 neutrinos should be signal enough that one is building up in the right way from pre-geometry without starting to calculate particle properties. And 5, one might speak of a, quote, logical structure of the universe in the sense that yes-no does it all. Logic means calculus of propositions, too. Wheeler was searching for philosophical principles, and he was guided by the physics of the collapsing star. The creation of a black hole tells one that physics must follow down to the tiniest dimensions. At these dimensions, fluctuations of geometry annihilate our concepts of space and space-time, such that even geometry must in some sense be a smooth approximation of a complex structure. If Wheeler was on the right track, geometry, electromagnetism, and a non-classical two-value neutrino should emerge from free geometry. And building from his earlier statement that the answer may be found in binary, Wheeler realized that logic means the calculus of propositions too. This is the last longish quote, I'm sorry. Is there an isomorphism between free geometry and the calculus of propositions? I have often spoken of the idea of a floor covered with white paper and ruled off in 1-foot squares, and someone down on his hands and knees writing in each square a set of equations for the universe. And the question, what makes one set of equations put on wings and become airborne, while all the others lie on the ground, dead? But the calculus of propositions is marvelous. It is not only free geometry, it is also free number. If one is looking for something beautiful and uniquely right, what else could there be but this? Then even the quantum principle would be seen as part of a larger whole. The worlds of mathematics and of physics would become one in a flash. So we moved now from three different ontological sort of principles or ontological pictures that Wheeler has developed. And they follow along in sort of terms of increasing simplicity. First, there were 3 zero rest mass fields, then one single geometrical field, and then something yet more basic and simpler, the calculus of propositions. Wheeler's specific proposal about the calculus of propositions wasn't ever really fleshed out. He had scattered notes about sort of taking averages over long streams of propositional statements. And so, again, because simplicity was a constant over time and the ontological picture changes, I'm concluding that Wheeler's epistemic strategies led his ontology because he knew in order for something to be true, it must be simple. He chased ever-increasing simplicity. This drove his ontological progression. Thanks.
So now we have about 10 or 15 minutes of commentary by Helga Kraut from Harvard University, and then we'll have questions after that.
Yes. Well, obviously, these two papers by Tillman and by Aaron, different, that deal with different persons, that deal with different periods, but also obviously they have a great deal in common, insofar that they deal with unification. That they deal with this age-old desire for unity, which certainly was common to Wheeler in the 1950s and Einstein in the 1920s plus. And it deals not just with any kind of unification, but the most unified and the most deepest form of unification one can think of at all. So it's a hugely ambitious project these two gentlemen were involved in. I think it's important that one realizes, and it didn't become very clear in either of the talks, that this is part of a very long tradition in history of science and ideas, which literally goes back to the Greeks and up to the present. The quest that some modern physicists are engaged in, such as string theorists, other persons engaged in quantum gravity, is the same quest. And one of the differences between the two talks and the two unification attempts is obviously related to the fact that Einstein did his work in the 1920s and Wheeler in the 1950s, and the scene of physics has changed very considerably. Einstein and his contemporaries in the 1920s could afford the luxury, or thought they could afford the luxury, to disregard quantum forces. So when Einstein speaks about unified theory, he means a theory which unifies gravity and electromagnetism. And that certainly is difficult enough. But when what Wheeler was after in the 1950s and 60s had to be, was a theory which also included the two other fundamental forces. Incidentally, I believe that this made us so standard a distinction of the fundamental interactions in four classes, the strong, the weak, and gravity and magnetism, only emerged in the 1950s. It's only then that people begin to speak about these four forces, which they still do, of course. Yes. I'd like to say a few words about Aaron's paper and perhaps a little more than about Tillman, the reason being that I was able to read it in advance. And also that the two cases differ, of course, in the sense that there has been written quite a lot, not a whole library, but a small library maybe, about Einstein and others, attempts at unification, Eddington, Ryle, numerous others in the interwar period. As far as I know, next to nothing has been written about Wheeler's speculations, and perhaps speculation is a better term than theory. And indeed, I mean, this work is based on his notebooks, which are incredibly fascinating, but also a bit problematic. And I must admit that I find, Wheeler's notebooks, which obviously are made for private purposes, and that's important to keep in mind. So it's unfair to criticize him. But it is as if Wheeler had no idea that other people have thought the same source as we have. And there were other approaches. He was part of the tradition. Apparently he doesn't refer to anyone. It's sort of very isolated, very private, something going on in his own head. So I'm missing a bit of the context which goes outside Wheeler and places Wheeler's ideas in the context of earlier and contemporary physicists. Let me just illustrate it, because there is some connection. In some of his early reflections in his notebooks, in the 1950s, maybe it must have been, Wheeler speculates about this problem of producing particles out of a primitive continuum, a vacuum. And this seems to be very much the same problem that Einstein first attacked in 1919 and later returned to in the 1920s. How can structures come out of the structureless? And that again was not something that Einstein invented, not a basic problem. One can find it in the ancient Greeks, but then one can find anything there. And one can find a beautiful example of it in the so-called vortex atom of the 1870s by Kelvin, in which he and other people, mostly Britons, tried to show how atoms could be conceived as structures in the continuous system. It's the same question. Another example is with regard to Wheeler, that in some of his notebooks he stops and he sort of realizes that perhaps out of his equations, which he doesn't write down, but he imagined that this unified theory will result in a lot of solutions and perhaps in a lot of new elementary particles. And then he says to himself, all which is possible must be realized in nature. And he doesn't, well, perhaps he realizes it. It's impossible to say. That is just part of a long historical tradition. Maybe he has reinvented this, which is the history of ideas is known as the principle of plenitude. A principle which certainly goes back to Leibniz and has played a very important role throughout not only the physical sciences, but the science generally, it still does. kind of that Wheeler wrote, for instance. Gion had used it, or implicitly used it, in order to argue for the existence of positive electrons and magnetic monopoles. He said that because these particles are possible, meaning they are consistent with quantum mechanics and relativity theory, then they must exist in nature. And the last, next to last point I want to make is the radical conservatism, which you rightly underlined. It seemed to be, and Wheeler seems to be very much aware that he was a conservative in a certain sense. And conservative means that, as far as I understand, that he didn't want to change in anything the foundation of quantum mechanics and relativity. These are sacrosanct theories. But how original was this idea at the time? I don't think it was very original. At about the same time, we have Heisenberg embarking on his failed attempt to create a kind of theory of everything to create a Mills formula. Something he did in the years about 1960, first in collaboration with Pauli, who soon distanced himself from this project. Then he had to be a Gion and other collaborators. And Heisenberg, he also underlined that he was a conservative. And so has later physicists. Nowadays, string theories and so-called blue quantum gravity, for instance, when they discuss, they emphasize as a merit in their own theories that there's no new physics anymore. It's good old physics. They are conservatives, and they argue who's the most conservative. Then there are some points I will say that I listed, but I just wondered about the connection between Wheeler's ideas to other ideas in the period. Because he is very much occupied with the vacuum, and says he wants everything to come out of vacuum or nothingness, which is something totally different, but forget about that. But he doesn't relate to contemporary ideas of the quantum vacuum. He doesn't relate to the idea that we can have zero-point energy in the pure electromagnetic field. He does mention that these are his notebooks, the Epistemic method, which date from 1948. And by 1960, it was verified experimentally, and the general explanation of it was that it is a manifestation of the energy density of the vacuum. 10 years later, again, we have the connection to the cosmological constant, and then eventually to dark energy. All these, or some of these ideas seem to be implicitly, absolutely implicitly, but floating around in the head of Wheeler in the 50s and 60s, but it doesn't apparently relate to basically the cosmological constant at all, although it was known at the time to represent, or could be represented as a manifestation of the energy density of the vacuum. So I'm just saying that there are many contexts and many aspects which are related to these two concepts. Thank you.
So, did we have both speakers join? Okay. You might want to stay. There might be some comments. No? Okay. And perhaps the speakers would like to address some parts of the comments first, and then we'll open to questions. And if not, just tell me.
Okay. Well, I want to start off by thanking Helga for his detailed comments. As organizer of this session, it was more than I had hoped, so thank you very much. I think the primary issue you raised was the connection of Wheeler to other ideas, older ideas, contemporary ideas. And I think this is something of a puzzle for the historian as to how it was possible for someone who was having these ideas to be so, in a sense, isolated. He did do some looking around. He did, for instance, consider Einstein and Rosen's bridge paper, and then eventually reject it. And the lack of mention of the Casimir effect is definitely conspicuous. I don't know if I have an explanation for it. So there's a tension for me in how much to bring into the account that it didn't seem like Wheeler was himself engaging with. That's probably, and I just wanted to make a small, maybe it was misleading in the paper that I wrote, but when Wheeler says that anything that is possible must happen, there are echoes of that in his notebooks, but the actual strongest statement of that is from an autobiography that he wrote, so it's close back.
Well, I have a question that's also related to Wheeler's work. So, it's the fact that he has all these graduate students, it really seems to be key to Wheeler's work. And the comment that you made on his conservatism. So I just looked at this new book of Everett's, the early Everett papers, which are just from that period. And there's also this correspondence between Wheeler and Everett, and where Wheeler really tries to push Everett's dissertation vis-a-vis Moore. I mean, he's willing to entertain, Everett's position, and he writes his companion paper where he's, not at all conservative, but it's with respect to the graduate student.
Yeah, but if you read contemporary writings on the Everett position on quantum mechanics, they claim that it's very conservative. They claim and they say the Everett interpretation is the most conservative interpretation of quantum mechanics.
But in the Wheeler paper, the companion paper, he compares it to Einstein, Newton, and those other revolutions.
Yeah.
Okay, questions from the floor? Yes.
Two questions about outside influences. The first one to Aaron, or as two parts. Undergraduate students, then later postdocs, also a source of possible influence. And what influence would the outside world, because we had a very specific way of working with them. And I was wondering about von Neumann. I mean, what's the context of this letter to von Neumann? Because is he interested in doing propositional logic as one thing, as von Neumann was quantum logic? So that's my question to Aaron. And my question to Tillman is for your final debate about Einstein being skeptical about the variational principle. I mean, has it to do that he sort of saw Hilbert's program in 1915 got stuck physically with this variational principle that it was pretty naive? So is it some suspicion that if you just put together relativity and now a more general electrodynamics with the variational principle, that's not really the way to go?
Okay, so as to influence from graduate students, absolutely. So, for example, I spoke about the influence and work with Charles Misner, and in his notebooks, he records, following conversations with Joe Weber, I have been thinking about this. So there's definitely a sense of intellectual exchange. Wheeler often reflected on pedagogy and how important it was to him. He felt that the best way to learn something was to teach it. This is why he was so excited in 1952 when he was given permission to teach relativity, which he had never done before, never published about, because he saw himself as in a position to learn the subject as he taught it. As to von Neumann, that correspondence is quite a bit earlier, dates quite a bit earlier to Wheeler's interest in logic. He did reference and appeal to some modern logicians and made an effort to go and speak to them at conferences and things like that. But I don't have any more. I don't think there were any more letters to von Neumann that I'm recalling right now. So it's not an extended correspondence. But I think they must have known one another through the national security world as well.
Okay. Yeah, well, I don't think that that any opposition to Lillard or his program is already. I think there's always in Einstein's work he's pursuing either the path of doing some way of directly coming up with field equations or with variation formulations, and it's an either or. He never, I think, gives up on the variation formulation for principal reasons. And in this case, he gave up because of problems of that particular approach to account for the outcome, and that also repeats itself later. In fact, I taking out my neck again, I think he's following up the other program, even if he wouldn't say so.
Another question from the back, and then Priscilla. Sorry, could you stand? Hard here.
So I've got a question concerning your big claims at the beginning. So one of them was you said this C for unified theory was not driven by solving any open problems and so I'm wondering, wasn't that the case also for special relativity? Because the unification, I mean, Minkowski introduced four vectors a couple years after Einstein published special relativity, and he said from now on time and space shouldn't exist anymore, but only a combination of space-time. So the unification actually came after a couple years afterwards. The problems were solved already.
That we can see, yes, but yes, yeah. So the conceptual breakthrough in 1905 was in response to conceptual difficulties, right? And then a few years later, Minkowski's work kind of framed us into it. That we can see, yeah.
First one.
Well, I'm sort of asking the opposite question about your initial claims. Sort of surprised that you see, especially in the documents you present there, that you see sort of just a sort of general sense of unification as the main motivating factor, right? Because, in all those documents, he very explicitly addresses the question of, the structure of the electron, right? And that was, of course, an old and very important point, right? That's what the electromagnetic program had failed on, right? That was sort of the central question that Einstein had grown up with, and I don't think he'd forgotten about that, right? And in all his many theories that he goes through, that's the first test case, right? Can you construct a solution that corresponds to the electron? So it seems to me that and that of course then get mixed up in the 20s and 30s with the question how to understand quantum mechanics, right? The question that for him somehow also I'm sure had to do with each other, right? And the particulate nature of the electron and the discretization that quantum theory implied. So it seems to me that sort of is the main motivating factor, right? That electrodynamics was an incomplete theory by its own account, right? I mean, there wasn't, it couldn't explain, it couldn't give an account of its own foundation. So that was obviously an open theory.
Yeah, I agree. I would add that also that motivation kind of falls under the category of unity, because he wants to unify fields and map them. He wants to kind of come to a unified description that has no longer dualism between matter.
Yeah, but it's not just unity by its own sake, it's just the open questions of electrodynamics, right? I mean, it's just the unsolved problems of electrodynamics.
This is the second part of the response would be, so in a way it falls under the unity, what I would vague unity, overcoming the dualism in this case, not just gravity, the magnets, the field, the particles, the field, the matter. And yes, I concede that it's vague is too strong a word. It does have very concrete application, but it does not have a problem to solve.
problem of accelerating charges, I would say.
Another question here.
So this is a question for Aaron, and responding a little bit to what Elder said about, well, it's not particularly fair to use the notebooks to come to a conclusion as to some of these opinions because they were meant only for private consumption when it comes to Gion. But I was wondering, do you see connections, or have you had time to investigate connections between what he's writing about, what these sort of ontologies that he's developing in his notebooks, and what sort of topics he's choosing either to assign to his graduate students or to investigate for himself? And I don't mean you see this coming out in the scientific paper in some explicit manner, but rather do you see topics correlated with these changes in ontology?
Well, I guess first a comment about using the notebooks. I mean, they were private notebooks, definitely, but they were also something, the content of which was a part of Wheeler's social circle. So I end the written version of the chapter with quotations from a parody article that a bunch of Wheeler's students and colleagues wrote together under the pseudonym John Archibald Weiler. And it discusses things like his preoccupation with Leibnizian monads and his tendency to frame things in terms of, these paradoxical statements: mass without mass, charge without charge. They write monads without gonads. So, and this was actually published and is available online if anyone's curious. I will send you a copy. Glorious back file of the early general relativity journals, early, mid-century, early. So, though these were not published works, I think some of what I discussed was from published works. His paper with Misner, for example. It was clearly a real live part of his scientific life. It wasn't solely a private expression, but it was a part of his social circle. I haven't looked in detail at how he gave students dissertation problems. I actually think my impression is that he gave the students quite a bit of free rein, which is how you could end up with someone like Feynman sort of reinventing quantum mechanics, and someone like Everett reinventing quantum mechanics under his watch. And then you had Misner's original dissertation was going to be this project about recovering electromagnetism from general relativity, but Percy Bridgman, I believe, pointed out to Misner that actually George Reinich had done the same work decades earlier. So he was given a new task, which was to complete a Feynman quantization of general relativity. He made great progress on it. The ABM formalism, the M is for Misner, if you follow quantum gravity.
Yes.
I just wanted to comment on this question of electromagnetic worldview. Einstein's occupation before 1905 was not the electromagnetic worldview, it was atomism. And he felt that the electromagnetic field, as Einstein presented, had too many degrees of freedom. And that one of the motivations for the photon concept, that with many problems by introducing atomism into electromagnetic fields. So I think electromagnetic worldview for Einstein is not exclusive question, but how to extend atomism to the electromagnetic.
Okay, last question, and then I think there might be coffee hiding somewhere. I'm not certain. I'll be on the first floor.
The question concerns the shores because Einstein read the metric because the geometry and the geometry. The problem we know that we can't change his mind about Pythagorean and he made by special space he use special space. He don't need the metric. So he can do the same condition for Pythagorean without use the metric. So my idea, why Einstein didn't really anticipate this kind of geometry, because if it's necessarily, and we can do particular equation, very easy for particular equation, there are two parts, you don't need metric on the part. So why still the metric have to change as a geometry result to the geometry? Because usually the paradigm is metric.
Well, I think, understand correctly your question. I think this is what Edison does. Edison tries to show the theory that no metric, no space in this image. And then Einstein, in the course of elaborating these consequences, puts the magic back in, because at some point you want to have a magic. You have simplification. Either it comes out of the formalism as wants to have a Ritchie tensor from the connection, or you put it in terms of spinning.
No, but you see, by using 36, the list for quantity theories, the idea that it is mine, he uses subjective. So he's the subjective geometry. So he tries to construct the theory from a subjective point of view, that theory from it. So they have many things in this theory. There's a problem that people don't know how to think that we're using interpretation. Because we can do geometry without geometry more aesthetic, and even the equation is better generalized in the surface. So that's
Okay, thank you everyone, and there's one more session in this symposium to follow after